Okay, I think it's time to start the second half of this parallel session number 1 about healthy soils. So please be seated. Thank you. Here is our first speaker is already here. So in this second half, we will have the same structure as in the first half. So first we will hear 2 longer keynote speeches and then 3 shorter comment speeches. And we aim to have a couple of questions from the audience after each of the speakers. If you have any questions, then and you can also ask them in the chat in event there if you don't want to ask here or if you are following us online. So first, I will give the floor to Professor Claire Chenu from INRA and AgroParisTech, and also Claire is EGP Soil Coordinator. Welcome, Claire.
Thank you, Elisa. Good afternoon, all of you. Well, it's really a pleasure to be here. So thank you to the organizers for inviting me to talk to you about soil organic matter, my preferred topic, of course. And I would like to talk to you about the contribution of soil organic matter to soil health. So first, I'm an academic, so I like to define terms that we use. So first, what I will do is define soil health. Actually, it has been defined. It is defined as the actual capacity of soils to provide ecosystem services. This is the definition that is currently being used by the Soil Mission within the soil strategy and will be used in the future soil health law. Now, how does it relate to soil quality? And I like very much the work that has been performed within the AJP soil in the Siren project led by Jack Faber, where you see this graph with the, true difficulty target, the axis of ecosystem services provision level. So soil quality is the capability of soils to provide ecosystem services depending on soil type, land use, etc. Well, if you were there yesterday evening, the pale beige cake had not the same quality as had the 2 layers vegan chocolate cake. Very different. Now, soil health is the current soil status and ecosystem management that can limit the provision of ecosystem services. So soil health is less than soil quality, but soil in good health, its health equals quality, and well, you can refer to human health in the same term. Now, you can increase the quality of a soil with external inputs, irrigation, heavy, intense fertilization, but these can be unsustainable, and this has to be put in mind. So soil health, the current capacity of soils to provide ecosystem services, and soil organic matter actually is key to both soil quality and soil health. And here, well, a very schematic graph of soil organic matter, and it influences a number of soil properties: water retention, cation exchange capacity, aggregate stability, soil porosity, penetration resistance, and provides nutrients by mineralization. So contributes to primary productivity, nutrient cycling, biodiversity and habitat provision, water purification and regulation, and climate regulation. Essential, all the essential soil functions. And where should I point at? Here. I represented here soil biota, so there's nearly all soil functions that are affected by soil organic matter involve the interaction with soil organisms. So very strong interaction. And by the way, of course, it's the case, so you have properties. So it's there. Properties that are directly a function of how much of organic matter or a given subfraction of organic matter you have in the soil. It is direct relationship, it is static. And you have properties that depend on the biodegradation and mineralization of organic matter, such as biodiversity sustaining. In this case, it's indirect and it's dynamic. And this goes to this well-known, I don't remember the word, but well, soil organic matter, should we use it, mineralize it, should we hoard it, prevent its mineralization? And I think the talk by Nico Eisenhower this morning gave an excellent example that you can have both. When plant biodiversity increased, you had an increase in soil organic carbon stocks, but you also had an increase in microbial biomass, microbial activity, basal soil respiration. So it means that both were increased. So you can achieve both. Also on this graph, I think what can be seen is that soil organic matter being central to many soil functions, it is quite natural that many have thought of using soil carbon content as a unique indicator of soil health. And this needs to be discussed. Now, what type of do we have any quantitative relationships between soil organic matter and soil function or ecosystem services? So when you raise this question, you have to think that you have soil organic matter that affects a given soil property, for example, water retention, that determine a given soil function, for example, water storage, and ecosystem services, saving irrigation water or reconstituting the water in aquifers. First, you need a relationship between soil organic matter content and the property. These can be statistical models, we name them often pedotransfer functions, or it can be mechanistic models. Then, at some stage, you need an evaluation to state whether the level of the property ensures the desired provision of the function and ecosystem services. So you need to define critical values, thresholds, and for that you need a reference framework. One example of a relationship with maybe the most desired property and function was supporting primary productivity yields. There are a number of meta-analyses showing relationships between soil organic matter, usually soil organic carbon as a surrogate, and yields. These relationships are significant. They are kind of ugly, I would say, as you see on the left for you. And in fact, they are quite elusive. And several reasons for that, because first you have those feedbacks. The more soil organic matter, maybe the better soil fertility, so the better the yields, but the better yields, the more inputs you have, so that increases the soil organic matter content. Second, in many of these situations, and it's exemplified in the papers that I quoted here, there is also fertilization, mineral fertilization. So this complicates the analysis of the relationship. So what is it? Ooh. It's not that nice. Well, what I did put we performed at INRAE an expert assessment that we named the 4 per mil expert assessment. And one of, I was involved in several parts, but in particular in this one, relationship of soil organic matter to soil functions and properties. And here you have in this table, so I'm sorry, it appears very difficult to read, chemical properties such as cation exchange capacity, increased surface charges and chemical reactivity, physical properties, water retention, porosity increase, mulch at the soil surface, and biological properties. What I did put also in this table is whether the relationship is static or dynamic. What are the effects on soil properties? For example, increasing cation exchange capacity increases the retention of a number of nutrients, and whether what is the outcome? And the outcome you see, this I know that you can see. In most cases, you see it's green, so it's positive, but there are a few cases where it's not. Decreasing water quality or increasing greenhouse gas emissions. Then the column after states whether there are quantitative relationships available in the literature, and you see they can be model or they can be pedotransfer functions. And then the last column is whether this is important for all soil types. And for some soil properties, it's essentially important for some soil textures, so not all soils. For example, increasing water retention is essentially important for sandy soils. Things that you may note I don't know if yes, examples of relationship, cation exchange capacity. I choose an easy one. You see the statistical relationships, well, these are 3 from the literature, always clay and organic carbon content. So basically the same features, so they inform the same way. Now, another thing I'd like you to spot is concerning biological properties, nearly no quantitative relationship. You find no quantitative relationship between the abundance, the diversity of soil biota and soil organic matter content in soils. Now, in this expert assessment, what we did is that we used a number of pedotransfer functions to estimate what would be the effect on some soil properties of increasing this organic carbon content by 0.4 per thousand, 0.4%, so 4 per thousand annually during 30 years. And these are the results for soils with contrasted textures. And actually, well, it's disappointing. It's disappointing. You see very small relative variations, but still you see a strong effect of soil texture. That is, sandy soils benefit more than silty or clayey soils. Basically, the organic matter replaces the clay here. So what explains that? I think there are several explanations. One can be that these are not good pedotransfer functions. Indeed, a number of them have been developed using B horizons. But that's not the case with the ones we use. We're very careful. Another interpretation can be, though, these are not the relevant soil properties. Indeed, infiltration rate, drying rate are very relevant. And we did not quantify, did not find pedotransfer to inform them. But I think that the main explanation is that these are individual soil properties. And there probably are emergent integrative properties that come from out of small variations in these individual properties that we do not capture here. And this was referred to this morning in the talk by Ivo. I think nature is not only the sum of, does not act separately. I don't remember the sentence exactly, but it was exactly that. So emergent properties that, what I notice when I visit farms, discuss with farmers, is that they often say that soil richer in organic matter is better because it's easier to work with. So what is behind the easier to work with? Can be more workable days, can be better soil structure, can be more resilience. And I think we, with this approach, the approach I took, we do not capture that. And I agree with Lisa Petiola that considering soil structure probably is a way to approach this integrative effect of organic matter on soils. And I think that the visual description of soil structure, visual evaluation of soil structure should be used more and should be developed and improved for different pedoclimatic contexts. And from that, it was clear for the team of Pascal Boivin developed an approach where they quantify the ratio of soil organic carbon to soil clay, and it appears to be very well related to a number of physical properties, including the visual observation of soil structure. So more to do in that direction. But are there still integrative properties that react to soil organic matter content related to adaptation to climate change? There's not that much work, in fact, although we always claim that organic matter helps to adapt to climate change. There's not that much work. I like very much this study. I already showed you the graph on the left, the yields variation with organic matter stocks, so hence organic matter contents as well. But I'm interested here on the one on the right. You see that interannual yield variability decreases as the organic carbon stocks and organic carbon content increase. So that's interannual yield variability. It can be pests, but can also be climate variations. So I think this is a good integrative property for adaptation to climate change. And indeed, again, there's not enough data, but I think this shows clearly the effect of organic matter. Now, how to set organic matter critical values? So first, yes, I will present you a work that we're developing in the AJP soil. And first, so I'm, Elisa said it, I'm the coordinator of a European joint program that stands for AJP soil. That's, its complete title is Towards Climate Smart and Sustainable Management of Agricultural Soil. So it's a big program, 24 countries. And we have a diversity of activities, knowledge development, we have calls, we have now 26 internal projects, 18 external projects. We have activities of knowledge sharing and transfer, activities on knowledge harmonization, data harmonization, database harmonization, soil mapping, and knowledge application, including support to policymaking. So, what do I, oh, yes. Support to policymaking. So we are in the context of the development of the soil health law. And what we are doing currently is working on what are the approaches to set critical values for indicators. Critical values can be reference values. What are the usual values of a given indicator you find in a given pedoclimatic context and land use? Can be target values. What do you aim for? You consider as desirable. Or threshold values. What are the values of organic carbon content you would not like to go below because it's critical? And so we did some work together, and we had organized policy workshops, and we recently organized a soil health indicators webinar that is online if you're interested. And what we did, well, we discussed selection of indicators, etc., but also how to set, which approaches to set reference, target, threshold values. And I will present 4 of these approaches, or the 4 approaches we identified. First is to use fixed critical values. One example, in Germany, the table at the top left, where you see there's texture, there are values of organic carbon content, there's texture, there's climate. These were based on assessment of water retention, capacity of soils in the German context, and penetration resistance. So it's based on properties. And then they propose, you see also that there's a minimal value and maximal value. What a maximal value? Is more the better? Well, no. They integrated the fact that in organic matter-rich soils, you can have leaching of nitrogen. You can have losses of phosphorus. So the upper value comes from that. On the graph on the right is a French example, an old one, where I would say it's fairly similar in the approach. Experts, pedologists developed based on the sensitivity of soils to crusting, and water retention developed an abacus, where you see organic matter content, clay content, carbonate content. And then after, there's an evaluation, satisfying, not satisfying, too low. And so these are fixed values, and it can also be developed in a different way. And you have here a graph from a paper by Hirschbeck, where it is based on the perception of whether their content was desirable or not by farmers. And actually, the ones that answered for this graph are more than 600. It's not, there were many more in the paper, but, and you see that, of course, red, orange, green, that the perception of whether the organic matter content is enough or not was dependent on soil texture. Okay, so fixed values appears fairly simple. It is linked to soil functions. You can link it to functions, requires context-specific references, and so the limit is, do we have the available knowledge? The abacus in France was only developed in North France, not elsewhere, for example. Second approach, to refer to natural land uses. And here I took an example, I redrew the draft from the work by Sparling et al., that considered that for New Zealand, that a target value should be 80% of the carbon content of permanent grassland. And then, how to set the threshold? Well, they considered that within a simplified lifetime of a farmer converting degraded arable land to permanent grassland should be able to reach this target. So the threshold was the minimum value that allowed, with modeling, estimated with modeling, allowed with ROTC to recover this target value in 25 years. Okay, so that's simple, you may think. It's not linked to functions. It needs to be context-specific as well. And are natural references available? Are grasslands natural? Do you have in every pedoclimatic context a good reference? Not obvious. So that's clearly a limit. Third approach, relative changes. There you do not have any reference framework, but you consider, for example, plots at time 0 after 5 years, and you decide that those that increase by 5%, for example, are good, green, while the one that did not vary, it's not good. Relative changes. Well, you may think, again, it's kind of simple to implement because it just uses the current values. You need no references. There's little knowledge required, little stratification required. It's not linked to solve functions. But, well, you have to think of, okay, which percentage fix for the desired improvement, and what about pioneers? How do you value pioneers with such an approach? Fourth value, critical values based on existing distributions of the indicator. That's also what Sparling developed in New Zealand. They considered, so they had the database of organic carbon stocks in New Zealand, and they considered that the target value was the median of permanent grassland. Arbitrary, but simple. And they considered that the threshold, the minimum, was the lower quartile of the distribution. And another example, in France, we estimated the organic carbon sequestration potential using the actual distribution of soil carbon stocks with our national monitoring network, and setting that, for example, it was the upper 90th percentile of the distribution. Not linked to function, again, and requires extensive data. And again, how do you decide it's the median, it's the lower quartile, it's the upper 90% percentile? This is to be said. So different approaches that definitely need now to be evaluated thoroughly and compared. So to conclude, I would like to say that, well, of course, to confirm the central role of soil organic matter in soil health, that it provides different ecosystem services, so trade-offs need to be assessed, to be considered. Also, I would like to say that what is available as quantitative information always refer to contents. Very little to quality of the organic matter or to distribution, spatial distribution of the organic matter. While, for example, protection of soil surface against erosion, coarse debris located at the very soil surface are very efficient, while if you want to increase the water retention, it's more mineral associated organic matter, and you would like that property to be increased along the soil profile, along the rooting, down to the rooting depth. So yes, there are quantitative relationships available, but only consider content, but they are needed. So we need quantitative information to sustain decision support tool with the limits I told you about, not targeting integrative properties. And I think what is needed right now is essentially a synthesis of the available knowledge. There's much available knowledge out there. So different approaches are available to set organic matter critical values, and they need to be compared not only for organic carbon, but also for other indicators of soil health. And on that, I would like to thank you for your attention and thank my colleagues from the AJP Soil. Thank you.
Merci beaucoup, Claire. This was really nice and comprehensive presentation about the importance of soil organic matter in the soil health and the carbon content. So, any questions from the audience? I think we can take even two. I didn't see any in the chat. Okay, well, we can move ahead. Go ahead and ask Claire during the next coffee break then. This was mine.
Okay. That's all I have to take.
Thank you.
Okay, thank you.
And next I would like to invite to the stage Tuomas Mattila, who is a farmer and also a senior research scientist at the Finnish Environment Institute, Syke, as we say here in Finland. And Tuomas will also tell us about soil health and also water management and carbon sequestration. I will give it to you.
Thanks. Nice to be here. I learned yesterday from Twitter that this is the soil conference where you can freak out about soil health and talk about it obsessively and nobody will get bored. So I'm counting on that, everybody. So I have a few big topics there: soil health, water management, and carbon sequestration. Two of these topics I've seen referenced here, soil health and carbon sequestration, and I know that water management and structure management has also been discussed quite a lot here. So they're all somehow interrelated, but how? Let's dive in. I would like to emphasize the last word there, which is the on farms, which I think has also been emphasized, but let's dive in with an on-farm approach there. So let's first start with something silly, I think. Where do I have to aim? There. There. Okay. For practical purposes, I'm wearing a mask. So if you want to know what I look like, there are generally two approaches to here. One is to ask an AI to summarize all known pictures of fins and make a pedo transfer function out of it, or a face transfer function, and make an approximation. That's not far off, actually. But the hat might be like overdue, and the mustache color is not quite right, but the main basics are right. The other option is that you can come tomorrow to the field in Kvidja and dig some holes with me, and I won't be wearing a mask, which is the on-farm approach, which I generally tend to prefer, although I am a modeler. So, there. So our on-farm approach to carbon sequestration and soil health revolves around 20 carbon farms, which are sampled every year. So each farm is split into two. Each field half has 3 GPS reference points, and then we sample 10-meter radius out of those. Collect samples, measure what's on the soil, measure infiltration, then do analysis in the lab. That's Andre there. Andre is doing his master's thesis on the nitrogen pools here, and yesterday the paper was accepted. So Andre, I have to say, what happened? Technological problems. A good time to advertise that Andre is looking for a PhD position in the autumn. So if you want to hire a really good person, then Andre is your man. Great. I have all kinds of different presentations here. Just going through. All right. So every summer we go driving about 2,500 kilometers, sampling this is the last year of the sampling route, which is one major reason I'm wearing this mask, because if I get sick, I'm going to mess up the 5-year sampling routine. But over this sampling, we dug about 1,000 soil test pits, did about 1,000 infiltration tests, and took about 6,000 sample cores from the fields. But that sounds like a lot of work, but actually the person doing the most of the work is there, that's the farmer. So this is a farmer-driven research where the farmers designed and maintained their experiment on their field on a voluntary basis, which is, I think, great. But once we dive into the results, we have to keep in mind that we are investigating farmers cultivating cover crops and not cover crops. So this is not a fixed experiment where we'd have a certain success rate of cover crops. These are farmers attempting to farm cover crops, and then we see what happens. So why look at those things at the same time? Because first of all, they are all connected, as we all know. But second of all, they have all changed at the same time over the decades. So if we look at the last 60 years, there's been a gradual decrease in the amount of soil carbon, which most of you are probably familiar with. Then at the same time, since the Green Revolution, there's been a gain of phosphorus. That's the sum of phosphorus balances from 1960 to 2020. So European soils have maybe lost about 4 tons of carbon and gained maybe a ton of phosphorus. And of course, that pool of phosphorus can be a very long-term high risk for eutrophication, which is, I guess, one of the reasons why Baltic Sea Action Group is one of the organizers of this event. And then, to make things more complicated, is that we have increasing and widespread soil compaction caused by machinery weight increasing by 6-fold during the same period. So we have a problem where increasingly compacted soils have accumulated huge reserves of phosphorus and lost carbon. And now we want to build carbon, avoid that phosphorus from getting to the water body, and hopefully fixing the hydrology, which has been increasingly damaged. A sustainable level for soil stress would be 50 on the right side. So, and to be honest, those are like maximum wheel loads, so it's not average, but let's say we've been walking on thin subsoil for decades now in Europe because of increasing machinery loads. So our carbon farming experiment is then done on compacted soils. There's a nice review on one soil in Sweden where they tracked like what has happened with the bulk density along the years. It started from the green and went towards the red, and as it got compacted, the root elongation rate dropped to half during that period, and now in 2010 the whole soil was more compacted than the plow layer compaction in the 60s. So compaction is widespread, and how it's visible in the fields when people start doing carbon farming is this. On the left, there's tillage radish, which is recommended because it loosens the soil with its strong root system, unless the soil is so compacted that it just finds the nearest crack and tries to survive. What's happened here? Down there is brassica, winter brassica, oilseed crop, which can grow roots to like 1.6 meters, unless it hits a compacted layer in 8 centimeters and just tries to cope with it. And there you see drainage lines, which are the only places where water infiltrated properly and which has good growth in the map. Other parts have poor growth, and that's how it looks like in the field. So trying to regenerate soils with carbon farming has to start with the kind of initial states. Soils are widespreadly and increasingly compacted, and the water cycle is not working. That's not the only problem they have. We have just kind of mapped out what kind of problems there are. The fonts are a bit small there, but how to say, the compacted layer was found in these survey soils like in 90% of the soils, and 60% of them had drainage problems, which is shown in green in the low amount of earthworms. No surprise considering the soil condition at the start. On to a more positive note. In theory, carbon farming could help. So a way, the most commonly used tool for carbon sequestration is increasing vegetative cover to build more biomass, which will be then transported into the soil as more residue, which will build more microbes and then stabilize more stable OM. And the same processes which build soil C can decompact soils, reduce phosphorus loss, decrease P balances, and improve the water cycle. But please remember the first slide, the AI average fin. So this can happen in a model, then what happens in the field is a different thing, approximated by the model, of course. This water storage thing was mentioned already. It's kind of, and I want to highlight like 2 things here. First is that we know that increased organic matter will increase the available water holding capacity. The estimates have changed a lot along the year. Quite often it's cited that it's like 1% of organic matter increases available water holding capacity by 3.6%, but it might just be something like 0.15 or 1.16%, which isn't much. But what happens with cover crops, which build soil organic matter is that you might see in a short period of time like an 11% increase in field capacity, because it cannot be reduced just to the organic matter or carbon chemistry. And you might see a 27 millimeter reduction in runoff based on a review, because you have more evaporation. So to summarize it, carbon farming changes everything with soil water. I know that that's not a very fair way to say it, but let's say it changes a lot with soil water. So in a compacted, shallow-rooted soil with low vegetation cover, you have lots of the rainfall leaving the field as surface runoff. And if you get the structure right, you get root channels there, you get much more both infiltrated, but especially evapotranspirated. So less water going out of the soil through runoff and more water leaving the soil through evaporation. When we move on to the fields, like from theory to practice, some effects are easy to visualize. So this is like 4 years of improved grazing practices, and we see that it has been successful in building biomass. There's a trampled layer of biomass about 8 centimeters thick on the soil surface, and the structure isn't that bad too. So like some effects are easy to visualize for some measures. We also see circled there ley farming, which means introducing grasses into the rotation. That also builds biomass and builds this so-called soil armor on the top. This then is seen also in more microbial activity, but not always and not in all cases. Like for example, in the carbon grazing, the microbial activity even reduced a bit, but with ley farming and cover crops, it increased a bit. Then we see, like related to the water cycle, more pores and higher infiltration. This on the right is pore volume, tells how much water can fit the soil temporarily during a massive flooding event or rainfall. And then we have infiltration, which has increased quite a bit. There's also a massive difference in infiltration between sampling groups, like the highest infiltration rates going to 120 millimeters of water per hour, and the poorest being just like a few millimeters per hour. So carbon farming seems to improve structure, at least in some cases. But then we could jump in also to look at the dynamics. We have in the fields now real-time moisture sensors, which have pretty good resolution. So we get for each field this kind of a year of cropping and what it does with the soil moisture. And it has some interesting things there. Like you can see that in the spring, after snow melt, it settles down into a certain field capacity. We can track this over time to see what happens with the field capacity year over year. Then when the soil is getting drier, you have diurnal variation between night and day. And then if you have a rainfall event, you can see how much of the water actually ended up in the soil and what was captured by the plants. And then if you zoom into the day-night cycle, you actually see capillary rise during the night and evapotranspiration during the day. So when we get the last sampling tour done, we'll start going through 5 years of these to see if carbon farming actually increased evapotranspiration or increased capillary rise and infiltration and such. But just kind of as a tip, modern technology, especially related to real-time monitoring of moisture, can really help us monitor what carbon farming or whatever farming does to soils. This probably doesn't work again. But okay, so we saw changes in many variables, but where we see very little change is in soil compaction. This is the VES from the previous presentation, where you do a visual evaluation of soil structure. So if the soil started out below the line, they were in okay structure. If they started above the 3 line, they were in a degraded structure. And there isn't a clear visual trend on what there would be happening. So soil compaction seems to persist, and as you can see from the photo, it can also like hinder root growth and hinder carbon farming practices. So it would be critical to improve the soil structure, and carbon farming by itself doesn't fix it automatically. Next slide. Yeah, so how to get from bad to good structure? There's 3 steps. The first step is to decompact the soil if it's seriously compacted and allow plant roots to stabilize it. So there's the red machine is a subsoiler, but the more important machine is all the green machinery there, which is the plant roots, kind of stabilizing the soil after it's been loosened. Then what needs to happen is to design the tillage chain or the machinery chain so that it doesn't compact the soil over and over again. Those are cross sections from a Terranimo soil compaction tool, free to use. That's one farm's all the machinery used during 3 or 4 years. That's like a 16-meter wide cross section of soil. And with the current equipment, there's recurring soil compaction events all over the place, meaning that almost all of the soil is traveled with soil compacting damage over there. Actually, the green or the dark green to yellow is the limit where you wouldn't want to go with soil stress. But with some kind of redesign, not intensive either, just fitting machinery widths, getting rid of plowing, and maybe changing a few tires, you can get to a situation where half of the soil is never treaded with an agricultural machine, and when it is, it's not causing serious compaction. And then last, you need to get drainage working. So the most land, agricultural land, has been drained, but we found in our survey, again, about 60% of the fields have drainage system failures. So there's a system, but it doesn't work. You get water coming up to the topsoil, and it's not good for plants or soil life. Okay, pretty concrete stuff. But fields are an abstract concept. I would like to kind of challenge this still. So we tend to focus on fields. How much carbon did the field sequester? What's the carbon balance of a field? But actual fields have a lot of variation. And the way to solve this is precision agriculture, which is usually just applied for fertilizer application, but it could just as well be applied for water and carbon as well. Here's an example from the literature where you have a field which has an average yield of 5 tons per hectare, but the compacted areas have a yield of 1 to 2 tons, and the well-structured areas have a yield of 10 tons, or 8 to 10 tons. I calculated the phosphorus balance there, but I guess that the same would apply also for carbon balance. So within a field, you can have different zones which are developing in wildly different directions. The map down there is again drawn by Andre, thank you, where there's the depth to water table is the contours, and then its yield is the colors. And you can see that as the depth to water gets lower, the yield gets worse. So it's kind of, fields are an abstract concept. So depending on where you sample and how, you will get completely different results, which is part of the challenge of tracking carbon. So as an overall summary, carbon farming doesn't fix the water problem by itself, but the water problem can be a serious limitation for carbon sequestration, so it needs to be managed. Deep-rooted crops are not deep-rooted crops if the soil is seriously compacted. And 2 take-home messages is that structure matters. So next time when you go to an experimental field, take a shovel and water bottle with you. Those will help a lot in figuring out what's going on. And also within field variation matters. So management zones might be a much better unit of analysis than fields by themselves. So there's 3 photos of soil structure, and like if you would apply the same carbon farming practice on each field, you would probably get radically different results. And the only way to figure this out why is to dig a hole and have a look. That's why I'm digging 200 holes again this July. So Sorry for the rant and kiitos.
Thank you, Tuomas. I think this was really great reminder of the importance of the soil structure and we heard many details about the water management and soil structure issues. Now we would have plenty of time for questions if there are some. There over there was one.
Thank you for that very nice presentation. You mentioned about soil compaction, and you showed the map where some areas of field had compaction. That probably is not because of heavy machinery, I believe. That is something else, right?
Yeah, a very good point. So the whole field was driven with the same machine, of course. So why some parts are compacted and some are not? Yeah. So there's a balance there too. So you have the soil stress and then you have the soil strength. And if the soil stress is larger than the strength, then it compacts until you get to the increased strength there. So those headlands often have drainage problems, or and moisture soil has lower strength. So it kind of creates a vicious cycle where poorly draining areas get compacted and drain even more poorly, then the yield drops, and then they start accumulating phosphorus, and then that phosphorus accumulates right next to the water body in a compacted soil. Yeah. But excellent question.
Do we have other questions? Huh.
Yes, I'm thinking to establish drainage systems is often pretty big machinery is used on the fields. So how do we get around this? It's like momentum 22, yeah. Because the heavy machinery that you use when you build a drainage system, of course, also causes the compaction.
Yeah, so there are like best practices around that. So one is to get the soil dry, or like install the drains when the soil is really dry, and basically the only way to get the soil dry, especially with non-working drainage, is evapotranspiration. So get a grass crop in there, wait until July, and then do the drainage, because the soil strength is much higher when it dries out. So that's one way there. But of course, then after drainage, it might need like reparatory work still. Yeah.
There is still one more question, and I think we have time to take it.
Yeah, I'm the scanning man. We've done this for 4 years, over 1,000 fields over these years. And to add on to what Tuomas very well described, once we have the topography and the formation where the surface water tends to go, the low spots, that's one issue. And then once we measure few layers of electrical conductivity, the EC value, we can define out from those relations which actually are the zones which are compaction prone, and the program actually can kind of guess it pretty well. We can find it if the drainage system is not working. The topography and the EC values actually give the same results, even that we don't necessarily measure the moisture directly. And once we take a reference sample out of that, we can kind of make it sure that this is the case. So actually the zoning is very important, because every field has always, we never find a soil without zoning or without differences. It's a very large flora of different things. So it's pretty demanding, to be honest.
Absolutely.
Short answer. Still, I give question to Galina.
Thank you, Tuomas. Really nice presentation. So I want to connect your presentation to the previous one by asking from you, and we can continue the discussion later, the question regarding, you were talking about soil structure, which is a very important thing, and it's a very practical thing from the farmer's perspective. And I want you to reflect a bit on what is the connection between the soil structure and soil health. How would you sort of reply on that?
Maybe it would be a bit like building structure and people health, in a sense. If the building has a leaky roof and is half full of water, then you can't expect people to kind of thrive in that kind of environment. So soil structure, in a sense, soil structure provides the environment for the soil organisms to a large extent. But of course, the soil organisms then can kind of do housekeeping in a sense that they can also build a better house by roots and such. I was a bit, bit strict with the subsoiling part there, because in many cases cover crops and crops by themselves can improve soil structure over time. So subsoiling isn't always necessary, but in the cases where the soil is like really badly compacted, then it might make sense to decompact it. So house and inhabitants would be the analogy I would like to use.
Okay, thank you. I think that was a very nice answer. Maybe we move ahead then. We had already quite many questions to Tuomas, and thank you. Now we heard two excellent keynote presentations, and after this we go to the shorter ones. But I would really like to do the same thing that Tanya did in the previous half. So please stand up all, because now we are halfway and we have had two really long presentations. And even though interesting, I think we need some like refreshing moment. Thank you. Now we have again blood coming to our brain. And as Tuomas said, it's very important to take the shovel when you go to your fields. And I think we hear maybe more about that. But next we will have the agricultural advisor from Norway. So Hege Sundet, I invite to the stage.
Yeah, thank you very much for inviting me to this historical meeting. My name is Hege Sundet, and I'm working at the Norwegian Agricultural Advisory Service. Can I have my presentation, please? Yes. When talking with farmers about soil health, I highlight the new perspective that soil health means that soil is alive. And this living soil and plants together build these biological aggregates. They build their habitat. Good soil health makes the ideal crumbled soil structure with stable, stress-tolerant aggregates. This structure supports plants and soil life and protects soil carbon from erosion and decomposition. Photosynthesis and carbon is the energy of this system, and that's why we always should cover the fields with living plants. When we recognize what soil health looks like, we know the direction and our goal. Soil microbiologists have determined that roughly 90% of the function in soil to perform are biological driven. This shows a simple slake test we sometimes use to demonstrate the importance of aggregate stability. The 3 containers contain soils from same field and have same soil texture, but different treatments. The soil in the right container is from bare fallow area, tilled and treated with glyphosate. The soil in the middle container has been protected by grain stubble. And the third container show the dramatic effect of cover crops undersown in grain. Growing cover crops is an easy way to perform aggregate stability. With this new understanding of soil function, growers can reduce and eliminate erosion, runoff, nutrient leaching, drought, and poor performance to be truly sustainable. The best way to understand soil health is to dig a hole and smell, observe, and explore the soil together. We invite farmers to participate in experience groups with a special focus on soil health. They learn visual assessment of their soil structure and parameters like water infiltration. These are two participants in the experience groups who learn how to examine their own soil with an infiltration test. Norway is a small but long and high country with large variations in climate and soil conditions, and farmers face many different issues related to soil and soil health. Local advisors have specialist knowledge of local soils, plants, and the farmer's context. We cover all production from fruits and berries to grassland and dairy production. For farmers and the society supporting soil health, is crucial to their long-term economic, ecological, and social bottom lines. And we have 25,000 members, farmer members, and we are 350 advisors in Norwegian agricultural advisory service. In NLR, we have an expert group in soil and soil health coordinating and serving the organization. I've been involved in several projects working on soil carbon farming and regenerative farming, how to monitor the health to support the farmers in regenerating their soil. And local advisors are a link between research and the farmers. Our traditional way of working is local presence, arranging field trials and field days, and the aim is to develop better practice for the farmers. The best way by testing new practices in field trials, we achieve less risk to the farmer when developing new practice. Everyone benefits from sharing new knowledge. The result of local trials are used in recommendations that take into account the farmer's context. And farmers can make direct use of new knowledge. I think soil health and a more holistic approach should become part of more field trials. And in that field trial, we looked at different organic matter as a soil cover, and as a weed. Okay. And it's important to, therefore it's important to test different practical measures. And in this last picture here, we tried different organic materials as a soil cover to achieve weed control, soil protection, and better condition for the soil life. Here, my colleague Kari is managing a large-scale trial on growing flowering strips in the headland of conventional potato fields. She found this to reduce soil compaction and to increase yield in following years. More insects were observed, and both beneficial and some parasites. And it's beautiful. When the farmers change their practice, new problems arrive. Many farmers converting to no-till or less-till regime experience problems with trillions of snails in their field. My colleague Maren and Else, working on conservation agriculture in cereal, experience more snails with no-till. This is especially a problem when the snail eat the cover crop seedlings or other crops planted in autumn. With little disturbance and good for food resources, the snails thrives. Hopefully, the predators will regulate the snails' population over time. In northern part of Norway, my colleague Are reports that the more dominant soil health issue is poor drainage. In many cases, the farmer renting land from neighbors, and they will not take the cost of better drainage when it's uncertain how long they keep it. In northwest in Norway, my colleague Maud supports a farm in their multi-paddock adapting grazing system. This season, she does the short-term monitoring together with the farmer and look at the leading indicators for regeneration of the field ecosystem. And this farm is a part of a national project using holistic management and the monitoring system ecological outcome verification to monitor regeneration. Well, my take-home message is advisory work is an important link between soil health and research and farmers. Local field trials minimize risk for farmers. We facilitate networking and experienced groups. Field days is important for sharing knowledge. Local advisors have specialist knowledge on local soils, plants, and the farmer's context. And advisors are part of national and international networks. To change agriculture, we have to learn from nature and cooperate like the mycorrhiza fungi in all directions, I think. Then we can store carbon and support each other. Yeah, thank you.
Thank you so much, Hege. You don't have to leave the stage yet. If someone wants to ask questions from you, if it's okay, we can have a question or two, if there are in the audience. Okay, there is one.
Kristina Börneheim from Svensk Kolinlagring. I just thought you said briefly that there is like the bit of a trade-off between economics and cover crops or something like that. But I wondered if you have also with your different trials looked into the long-term economic effects, like the profitability of the farmer for these different...
No, we have not looked at economics, actually. But we should. In the future, I hope we will.
Yeah, thank you.
That's a really good idea to where to go forward. Thank you so much, and I think we continue. I think it was really nice to hear that well, you actually have to go with the shovel to the field, and also this knowledge sharing in the field days seems to be important way of knowledge sharing. Thank you again, Hege. now I ask actually Jessica Johansson to the stage also from Svensk Kolinlagring to tell us about their 4 criteria for successful carbon sequestration. Welcome, Jessica.
Thank you. Yeah, I will try to maneuver all these things. So thank you for a very interesting presentation so far. And as Elisa said, I will talk about our project Svensk Kolinlagring and about our 4 criteria for a successful carbon sequestration that we have developed in Sweden. So we are a small not-for-profit organization, Svensk Kolinlagring. We started this project in 2019 after the 2018 super dry season in Sweden. We saw almost all of the crops just drying away. We realized that something needs to be done. So we hooked up. I work at Miljömatematik, the company there, and we hooked up with Alba Eco, who are also a small organization working with research communication, and we started together this Svensk Kolinlagring. And actually this year we are seeing this super dry season again in Sweden. I think it hasn't rained now for maybe a month and a half where I come from, in the south of Sweden. So it's really important questions, of course, in Sweden right now. So why do we do this at all? And what do we need to consider when we work with innovation projects like this Svensk Kolinlagring is? Maybe I forgot to say what we actually do. It's a carbon farming project where we build business models to pay farmers for working with carbon sequestration measures. And we need to consider this, of course, the planetary boundaries. They are developed at Stockholm University. And as you can see, we are way beyond the limits under many of the thresholds. And what I want to say with this picture is really that we cannot only focus on carbon. We need to focus also on biodiversity, on the nitrogen, the phosphorus, and on the chemicals, and also on land use. So we need to consider all of these things when we look into what the future of our future farming and food system should look like. And also we should not forget also the dietary shift that is needed for this to being able to actually happen. So we created a framework because we, as many before have said, that we need to take into consideration the local context. So we created a framework for Sweden. And we also have had a lot of help from our Finnish colleagues to help us with commenting and making it even better. So thanks a lot for that. And it is in Swedish now, but it's open for everyone to read. So if anyone would use it, would like to read it, contact me, and then I can send you a copy, and you can have it Google translated. This first version of the framework is action-based measures, and I only have 8 minutes, so I will not talk more about that. But what we offer to farmers is really criteria that needs to be transformative, of course. We need to have to make a change. But it also needs to be feasible. But what we don't want is to decide what type of methods and practices that the farmers should use. Like many other projects, or I would say all other projects like ours with carbon farming practices, carbon farming projects, then it's from the beginning decided, you should use cover crops, you should this and that, and then you get this and that much money. But for us, we said we don't want to build it that way. We want to build it to be more flexible, but still transformative. So what we have done is something that I think is unique. If we're not unique, please shout and we can connect. But we basically, of course, we are basing our program on these principles. And this is the same principles that you see everywhere when you talk about regenerative farming or carbon farming. So it's nothing new. Of course, you want to keep the fields green. You want to maximize diversity. You want to minimize the soil disturbance, and you want to also maximize photosynthesis. And what we have done then is that for every one of these principles, we have created a criteria, or set up a criteria that the farmer needs to do on each field that is within the program for every year during 5 years. So we do 5-year contracts in this first version. So you need to fulfill at least 3 of these 4 criteria during the 5 years. And the different criteria are exciting, and it's not working there. Okay, so for the first one, for first principle, then we have the criteria that the crops need to cover the soil to at least 70% more than 10 months of the year. And it doesn't have to be a cohesive period. 2 minutes already? Oh my God. Okay, I'll finish. And of course, all of these criteria will be needed to be evaluated, to be, and also worked on in the future. This is our first season that we are going from the pilot that we did 3 years to the actual. This is what's taking all the time. Clicking this one. Okay, so the next one is that we want to have at least 4 plant species from different genera must be grown on the field every year. So this is really important also from what we talked about today, that we actually have the biodiversity on the fields every year. And then, of course, we want to minimize soil disturbance. Yeah, and then we translated that into that we want to have year-round ground cover, so more than 90% of ground cover over 12 months. And then it can also include crop residues and other dead material. And the fourth one, with maximizing field photosynthesis, is that we want to have continuous growth on the field during the whole growing season. And of course, this needs to be locally adapted, as the growing seasons look very different depending on where you are. So this is then what the farmers need to fulfill. And that we then follow up that they actually do this every year. And what other things that I just want to mention as well that we are doing with measurements, of course, is that we are also doing soil sampling, of course. Like, you cannot have this type of project at the moment without soil sampling. So we do 1 sample point for every 3 hectares, and we do it also down to 60 centimeters. So those are our extensive sites. And then we also have the intensive sites, where we take at least 3 samples in every different experimental area. And then we do sampling every year, and then we take also down to 90 centimeters. And actually, we also do other measurements with the spade test. It's super important, and also water infiltration, of course, and then the mini EOV, so the ecological outcome verification. And this is something that we do together with the farmer. So it's super important that we use this as an educational tool to work together and learn more together with the farmers. Okay, so now I have 0 minutes. Thank you so much for listening. And if we are really open with everything that we are doing, since we are not for profit as well, we really want to collaborate and spread this. We are only working in Sweden, and we will continue only work in Sweden, but we really want to collaborate with others that are in their local context. So please reach out. Thank you.
Thank you, Jessica. We have still time for questions, couple of questions if someone wants to comment on these 4 criteria that Jessica just showed us. I think it looked very nice, the continuous ground cover and really enhancing the photosynthesis, and to me looked good. I don't see any hands up in the audience, so one. Good to use some time for questions because we sort of made Jessica hurry up towards the end so that we would have time for a question or two. Please go ahead.
What is the basis of recommending 4 crops in a year?
What did you say? What's the best?
What is the basis of recommending 4 crops in a year? 4 different crops.
What's the meaning is?
What is the reason? Why? What is the rationale?
No, because we want to promote biodiversity. As we heard here today, the more diversity, the more carbon sequestration, the better soil health, etc. So that is why we want to have at least 4 species growing on the field during a year. But of course, you can have one main crop, and then you have like a mixture of cover crops. So instead of having a cover crop consisting only of one species, then you have a broader mix with the cover crops.
Is there data to suggest that if you have 4 different crops, you have more carbon sequestration?
Yes. Now the others have to help me, but yes, there is data that shows that if you have the more diversity you have, the more carbon is also sequestrated. So, and that we have heard from earlier today. So, and also, even if it wasn't so, that it would enhance the carbon sequestration, it would still enhance the biodiversity. And that is as important, or maybe even more important than the carbon. So no matter if it's actually storing carbon or not, we know that it's crucial, essential, we need to have more diversity.
Yeah, so maybe I would like to elaborate a bit. So it was, I don't know if the question was more than why like 4 species. So I really understand that we heard at this point that the plant diversity is important. But did you select 4, for example, on the basis that it's still doable and it's like not too high number per 1 year, so that it's doable, but it would be like, for example, you said that it's more than 2 different species, so some sort of a compromise perhaps.
Yeah, exactly, and it was also 4 different genera, so it's not 4 different species. Like they can't be too closely related. So it's also 4 different genera, because that's also, you want to have to spread the functions as much as you can. So of course we would like to have you have to have 12 different species from 4 different families, etc. But we are not there yet. So I think in the future, of course, we want to have even more. Yeah, and also go from genera to families. Yeah.
Okay, sounds good. Thanks for clarification. I think we move to our last speaker then. Applause once more to Jessica. And our last speaker should join us online. He is Tom Rabaey from General Mills company about their regenerative practices adoption. So do we have Tom online?
Yes, this is Tom. Can you hear me okay?
Yes, we can hear you okay. So warm welcome to this meeting. I'm really glad that you can join us online. So go ahead, the stage is yours, Tom.
Okay, thank you very much. And I've really enjoyed the presentations that I've seen so far this morning. Or for myself, it is this morning. I got up at 4:30 this morning to participate. Sorry that I'm not able to be there in person. I'm hoping that you can see my slides. I work for General Mills, a large branded food company, primarily in North America, but we do have brands that are sold around the world. I'm responsible for our agronomy sciences team, which includes our plant breeding, genetics, some of our dairy science, biodiversity, and other agriculture sciences as well. And so I will jump right into some of the work that we've been doing primarily in North America on how we measure adoption of regenerative practices at scale. And what I mean by that at scale is moving beyond individual field into the supply regions that we buy our ingredients from. We're primarily a wheat milling company, oat milling, cereal baking products company. So our primary ingredients are wheat, oats, some of the fats and oils like canola, soy, sunflower, and also some dairy products. And so as the previous speaker had mentioned, regenerative agriculture principles that you're probably all familiar with, minimizing disturbance, both mechanical and chemical, and maximizing crop diversity, keeping the soil covered, and such, living root as long as possible in the ground, and integrating livestock where possible. And then we focus on measuring outcomes of soil health, biodiversity, water quality, the water that leaves the farm, and farmer economic resilience. And we have established what we refer to as pilots in our regions, where we go out and we provide grower education. We do a lot of one-on-one coaching through trusted advisors and consultants that work for our company as well. We build community through, like, say, WhatsApp and Facebook pages, primarily for these growers to communicate and learn from each other. And then we spend a significant part of our budget also looking at outcomes, where we are measuring soil health improvements, wildlife, invertebrates, bird, biodiversity, and also profit measurements. But how do we do that at scale? And so, if you think about, we buy grain, we might buy commodity grain from our own grain elevators that comes to our own mills, or we might be buying primarily processed ingredients from a primary processor. So a company that maybe just is converting wheat into flour, and we're buying that wheat then and putting it into our products. And so we know the regions that we buy this from, but we also know that growers aren't necessarily growing wheat and selling it to us or to maybe our primary ingredient supplier every year. It might be that they're growing it, other crops in their rotation, sorghum, corn, soybean, hay, or livestock on that same ground. And so, how do we go from measuring, changes to farmscapes? Oh, we have the individual standing in a canola field here looking for, bird species, but how do we know that we can go to a larger, to say the geographic regions that we're buying from? And so, as the previous speaker also mentioned, there's a lot of work that goes into current, soil sampling of soil health. And, as we go in, we're taking meter deep soil samples, and we're trying to identify all these, aggregate stability and water infiltration and doing, microbial activity. How do we eventually develop models that'll take us by using satellite imagery of agriculture practices such as no-till or cover crop adoption or animal grazing, serious modeling, and then maybe just rely a little bit on some high-tech of soil sampling for model verification. And the same can be said for biodiversity, and we're developing similar tools like that. We work with a consultant, out sampling flax fields for insect species, diversity. Here's that individual again who's looking at bird or, that are showing up in canola fields. But in the future, is there a way that we can look at like edge of field effects that can help tell us about changes in habitat, or growers that are putting in cover crops and then grazing them as well for that might increase diversity. We're also using some high-tech monitoring equipment with some upstart companies looking at microphones or lasers that can help us identify different insect species across an entire summer for diversity, and using audio recording units to monitor for birds and different bird species, and then using that to model changes on the landscape due to different practices. And so some of the tools that we've you might be familiar with these, but Optus, the operational tillage information system that helps us through satellite imagery. One thing we've learned is that satellite imagery, they store those images on farmlands, on farm fields for many years. So it's not uncommon that the companies we're working with 5 and 10 years, maybe, or longer, 15 years of back history of imagery, looking at practices, and then through modeling and ground truthing, they can tell us where the changes have gone from, a lot of tillage to reduced till to even no till. And then the other model that we use significantly is the DNDC model, the denitrification and decomposition model. That's a model that was developed by the University of Delaware in North America. It's been evaluated in numerous universities. It has over 450 peer-reviewed journals worldwide, where they're looking at how soils and the environment responds due to these management drivers, such as no-till and cover crops, and keeping living root in the ground over time. And so just a quick example, I've got 2 slides left. What we have seen in working with this one partner in particular that we've been working with, this is probably projects that's been going on for about 5 years now, and we've really kind of narrowed in on some great examples really in the last 12 months or last 18 months. But here's like one example that we really can point to. So if you look at, this is a region of Kansas in central the United States. And you can see by the scheme up on the right or on the left here, conventional tillage, reduced or no-till, varying amounts of full or low residue. And you can tell by, if we look at, and then maybe below here, kind of that residue cover over time. We can also monitor the tillage practices over time. And then this is modeled annual soil organic carbon change over time. But if we look at the graph at the very top center, and hopefully you can see that. So starting in 2005, this is how long they went back and did ground truthing over time and also had satellite imagery for. And you can see that if business, kind of like conventional tillage, conventional practice, business as usual, if the grower continued to do his normal practice, we see that soil organic carbon declines over time from 2005 to 2017 is when the study ended. And so you can see that, it's relatively flat to declining soil organic carbon. But through ground truthing and modeling, this has been verified as the grower started to implement no-till practices over time, and then in 2015 implemented cover crops in addition the last 3 years. You can see that through no tillage systems and cover cropping, modeled and ground truth soil changes in soil carbon stocks did indeed increase over time. And so this gives us reason to believe in this example that this tools that we have been working with this partner on developing can help us as a company understand what is going on in the landscape, and our practices, our education programs, our working with growers on regenerative agriculture adoption, are they indeed working? And we believe we can do similar work with like edge of field effects for insect and bird and biodiversity. And then also we're working with another partner on modeling water quality. So water that leaves the farmscape, so as the practices of no-till cover crops, what does that mean for water quality that leaves the farm or is maybe infiltrated through those practices? And so lastly here, the company we're working with is Regrow. They're a public company. They do have a website out there. You can see some of this information there, but these are regions that we buy ingredients from in North America, and so wheat and oats in the northern part, and canola, winter wheats in the south, dairy products in some of these other regions, corn, soy, almonds, and rice and other ingredients out in California. But just looking like so we just can just like a snapshot off the dashboard that they prepare for us. It's like how much of this ground is in conventional tillage or reduced or no-till. And how has that change been? Compared to 2019, we have more conservation tillage, 9% increase. And compared to the 7-year average, it's a 12% increase. We can also look at things like cover cropping, changes in fertilizer application, where we're seeing some fertilizer applications have been decreasing in areas. Greenhouse gas emissions, and again, these would be modeled emissions, where we're looking at the quantity and soil organic carbon sequestration coming off of these areas. And so this is how we have been moving forward in the last 18 months. We haven't done a whole lot of reporting out on that because I think we're still kind of testing this hypothesis and looking at this and backing it up with ground truthing. But this is the pathway that we're on, where we're looking at how do we go beyond measuring individual fields, as I shared earlier, because we don't buy directly from individual farmers each and every year. So oftentimes we're buying from grain handlers. So how do we know the regions, at least, that we buy from are improving based off of the education programs that we have in those regions? And so with that, I think I'm at time as best I can tell. Thank you for hanging in there with me from a virtual presentation point, and I'd be happy to try to answer any questions.
Thank you, Tom. I think it's really crucial that the big companies are on board in this change of mindset that we have been saying here many times that it is urgently needed. And personally, I was really delighted to hear that you are also monitoring birds. That sounds good. I think we can take one question if there is any for Tom, because Tom is not going to join us for the coffee break. So if someone wants to have a question for Tom, then please ask now. And there is one.
Hi, thank you for excellent presentation. My name is Raisa Mäkipää and I'm from Natural Resources Institute Finland, Luke. You demonstrated really nicely the carbon benefits of non-tillage system. Do you have any evidence what happens when you disturb such a system, when you do tillage for 1 year and then continue in a way or other? What proportion of the carbon gain is lost in 1 year?
It's a great question, and I don't have like an exact answer to your question, although we have seen in certain cases, particularly in this northern region that we source from, where we have seen where in extremely wet years, growers have gone back out and tried to use tillage to level off harvest machinery, ruts that have been left in the field, or they decide that they want to use more tillage to help dry out the soil. So we do, and we have seen changes in soil organic carbon modeled loss and also through ground truthing as well. So what you ask is we have seen through our modeling, but I don't know the exact numbers that would be attributed to that. I think one of the things that we all know is that permanence is the ultimate goal, carbon in the soil for hundreds of years to come. And that is often needs to be at the deeper levels, but yes, tillage can disturb that and release that. And we have seen that in one scenario that we've been modeling through this technology.
Thank you very much.
Thank you. Thank you so much for joining us online. So give one more warm applause to Tom. Thank you.
Thank you.
And I think here in Helsinki we are ending this session. So I really want to thank all our great speakers and the audience for joining to this parallel session 1, whether you were here during the afternoon or also in the morning. I really want to thank you all. And continue the discussions on these topics over the coffee break. We are all continuing here in the same big room, 3:30, I assume. I heard that the other sessions are running a bit late, so but hopefully we will get enough long coffee break. It's still 1 hour, almost 1 hour until we continue here. So please enjoy the break. Thank you all.